Hey everyone, today we're going to be going over some design for manufacturability. We're going to be going over sheet metal today. This is for ME557, our design for manufacturability class. So we're going to jump right into it for why sheet design matters. So it's all over the industries: auto, aerospace, electronics, HVAC, etc. It's hard to find an industry that doesn't use it. Maybe some defense companies. Prototyping, things like that, where it's not as important, but they're still going to be in there somewhere in some designs. So it's a good balance of strength, weight, and cost. Mostly the cost is an important one right there. Realistically, any shape you can make out of a sheet metal, you can normally make it. You generally can make it out of any standard machining CNC practices, but that's just going to be substantially more expensive than just bending metal into shape. So cost is an important one for why sheet metal design is important. It's important. A lot of automated methods in manufacturing will be able to use sheet metal. Send a sheet down a factory floor and just punch it, stamp it, cut it, and get your final product by the end without really much human involvement. So once again, brings us back to the keeping costs down. And I always say, another reason it's important is everyone at some point in time has used sheet metal in their life, whether it be the door for your car, the doors and body panels on your washing machine, dryers, things like that, electrical conduit boxes, I think the hinges, brass hinges, things like that are going to be stamped sometimes. So it's all over the place, so it's important to know about. A couple quick two common terms to know: kerf width. We won't use it too much, but it's an important thing. It's the material removed for the cut. So 50 thou saw removes 50 thou material. Gauge. So the thickness when referring to sheet metal is generally determined in gauge thicknesses. We'll see that in the slide right here. So common materials for sheet metal design. I don't think there's really limiting to why you only use the materials, but these are generally the ones that are going to be common. Shops are going to know how to work with them. So steels, your stainless steels, if you need more corrosion resistant, don't want to coat it afterwards. Aluminums, coppers, titaniums. Like I said, I don't see any reason why you couldn't use some nickel alloy, so a Inconel, maybe nitinol. There's some other kind of exotic shape memory alloys, things like that. But they're just not common in the industry right now, mostly due to their expensive price tag for just the material per pound. As mentioned previously, we'll do sheet metal. It's in gauge thicknesses. We can see right here, if you have a gauge thickness of 20. One thing to note, it's different across materials. So for steel is 0.9, aluminum is 1.02, copper 0.69, titanium is 1.27. So this is really just the naming convention that was given back in the day. So these were conventions for how to actually draw this material out from the machine and manufacture it, and how many times you needed to draw it from its original billet. So that's really where the numbers came from. So there's not really much. There's no direct ratio. If you say, hey, aluminum's half as stretchy as steel, then it's we want to use that value. Or it would be double the value. So you're going to see right here, gauge 28 is 38 and 41. Yeah, so aluminum is higher than our steel. But if we come down to, looks like right here, 13 is where we have a crossover, and then all of a sudden our steel gauge thicknesses become thicker than our aluminum gauges. So it's just something something important to note. Which looks like it switches back down. So there's not much math or science to it. You just got to know the numbers. All right, so we're going to be covering cutting, forming, joining, and there is finishing, but we're mostly going to be covering forming today. We'll go over cutting and joining quickly, just explain the processes, explain the methods that can be used. Finishing, that's universal for all processes. I didn't feel that it's really a sheet metal specific design or things. We're not really going to cover it too much. All right, so going into it, we have water jet cutting, laser cutting, and plasma cutting. So the water jet is going to work with an abrasive. Particles will get flowed into a high pressure water jet. That's going to blow into the material. The abrasive will cut through it, and that's your kind of working piece. Laser cutter is a really high powered light energy beam that's going to melt the metal away, and you'll have a compressed air blowing that molten metal away. And then a plasma cutter is going to be really high temperature ionized gas that's going to be blowing at the metal at a high speed. So this doesn't need a secondary, air or compressed air to blow the molten metal away. The plasma cutter will do it itself. And then we have sawing and shearing and punching and breaking. So sawing, shearing is pretty self-explanatory. Blade, move your workpiece through it. Punching, shearing, or punching and blank is basically the same thing, depending on what is your scrap or what is the important part. So just a real quick table right here showing some advantages, disadvantages. We're only going to cover these real quickly. Couple key notes. Laser, it's a pretty low wear on the machine. There's no moving parts, no abrasive parts like the water jet. No contamination. Disadvantages, it's going to be a little heat sensitive. Any plastic or any material that really can't heat up won't be able to use it. Any reflective material wouldn't work too well. Water jet cutting is high wear on the machine, so those are, they have their advantages for, you can cold cut. There's no heat going involved. You're not going to thermally warp or distort your metal. Plasma is very cost effective, but one thing that plasma is kind of notorious for, at least for maybe some of the thicker pieces, it's going to harden up the edges of the piece being cut. It's going to make further processes a little more challenging. Now, for sheet metal design, that's maybe not the most important thing out there because bending around the edges is not a big deal. You're not going to be punching anything near the edges, so the hardened material there doesn't matter too much. And pretty rarely are you going to be taking a end mill or a drill or something like that to the outer edges or even any part of a sheet metal design. That's just not how you work with sheet metal. So having heat hardened edges is not really that bad of a thing. And then there's sawing and punching. We won't really go over to punching is a pretty important one to note. It's really good for economic, high output, many large volumes of these parts. Just fast, repetitive. You'll just send your sheet metal down an assembly row, just punching. The only problem is it's going to require some custom tooling in order to get the exact punch and shapes that you want. Now, if you're just punching out half-inch holes, things like that, shops are going to have half-inch punches. That's not really custom tooling there, so that would be ideal. We'll get into a little later about why you want to stick with custom tooling. Or stay away from custom tooling, sorry, and stick with standard tooling. So forming, there's rolling. You're going to roll the metal between two presses that are going to shape it into its whatever shape you finally want it to be. It can be multiple passes. You can see in this one right here, pass 1, 2, 3, and 4 would make a box shape by the end of it. There's deep drawing, so that's going to be similar to blanking and punching, but you're going to actually let the material move into form a little bit. Rather than just straight punching it out, you'll allow it to be drawn in. So this would be something more for maybe a soda can. You're gonna start with a flat piece and draw out that whole cylinder. Maybe those CO2 cartridges, something like that, would also be drawn out. Maybe not for those because you're probably gonna want a little deeper, thicker wall thickness, but something like that where you really need a long, thin cylinder wall. And then bending. Bending's going to be the one we cover the most today. It's, I'd argue, one of the most important parts for sheet metal design. It's been around for the longest, so we'll cover it the most. And this is just your standard V punch and die. And then we have spinning and hydroforming. Briefly touch on these. Spinning is just going to spin a part and then move a tool to form it while it's spinning around. Then hydroforming, there's also vacuum forming. So hydroforming is you pressurize and push down onto our material here. Vacuum forming, which would actually be we pull in this direction over here. So obviously vacuum forming, you can only get so much pounds per square inch, 14 and a half, 15, whatever atmosphere is, where hydroforming you can get much higher ones. I will note though that while this cavity right here is going to be large and big, it maybe doesn't matter as much its surface finish as say for other processes where you're going to have a curve, or you're going to be conforming to the shape of the I wouldn't say a mold, but it is pretty much a mold. We call it a die here. So important thing to know for sheet metal design that's a little different from casting is this mold right here, when you're machining it and manufacturing it, they can leave some pretty gross, large steps right here in our machining if you're going to kind of cut a surface right here. So they can leave it like that, and then what's going to happen, your sheet metal will be nice and green right here. It's really just going to come in, it'll touch off the top points, and still create this nice curved shape right here. And it's not going to want to dig into each one of these grooves. It would be too much bending, too much deforming there. So you don't really need a really fine surface finish on this die right here, which is important to keep your costs down. Hydroforming is going to be used more for like car panels, things like that, where you do want to have a nice curved shape. So just to keep in mind, this die is not going to be as prohibitively expensive as you might think for a big, finely machined surface, because it's a big, roughly machined surface. So yeah, this is just our quick, spreadsheet here. Advantages, disadvantages, how it works. I think we're gonna mostly skip this. Important thing, bending's got spring back. We're gonna cover that later. It's simple, low cost. Yeah, we'll just skip that for mostly right now. So manufacturing processes: joining, welding, rivets, bolting, adhesives. Those are the four main ones. I'll point out rivets right here. We want to stick to rivets. Rivets are great. They're one of the cheapest options, especially for sheet metal design. There are options where you want to use welding and bolting, but it's not as common, and obviously you could use adhesive for some places, but most of the time you're going to want to try to use rivets in your design. If you're important note, for those that aren't familiar with rivets, they do not come off. You're going to have to drill them out effectively. So if you did need something to be taken apart and put back together at any part in the assembly process, you're going to want to use bolting. But permanent fixtures, riveting, welding is also permanent, but it's a little more costly to accomplish. And adhesives are they I think the big issue with them is that you're either going to have a really long dry time, which means a longer, more complicated manufacturing process, or the dry time might actually be really, really quick, at which point you're not going to have much time to set the two parts together, and unless you have good alignment features, you're going to possibly screw that process up a little bit. So I would say let's avoid adhesives in your design unless you absolutely have to. Once again, a quick summary table right here. We're not going to go into it too deep. It's just we don't have much time today. Important thing right here: bend radius and bend guidelines. So it's the best thing to use. What I found is there's not as many formulas and math out there. You can calculate these values, but it's the calculated values rely on so many variables that it's just tough to figure it all out and get accurate numbers. They're going to have to be adjusting things on the fly at the manufacturing shop anyway, so why bother with those numbers to start? Just adjust on the fly. But mostly getting ahead of myself right here. The big thing is to use industry standard values as your friend. All right, you don't need to figure out the perfect bend radius for this sheet of metal. Just use a 30 thou die. That's the most common for anything up to 1/8 of an inch. So if you're using a 1/16 of an inch or a little less, a little more, you're still going to be wanting using that 30 thou die, because any shop you send it to is going to have that die available. If you specified a 33.5 thou die, I mean, someone's got to manufacture that die now. That is now probably going to be even more costly than your sheet metal design. Real quick, the common machines for this type of bending are brake presses, what they're called. Big variety. There's these big industrial ones, the 8 foot long, 240 tons, $100,000, and then you can even go down to a hand-operated one right here. It's only 4 feet, 16 gauge max capacity, $1,000, and you're gonna have brake presses anywhere in between them. I will note on this side right here, just for any other manufacturing, not necessarily for sheet metal design, for all of us to be aware that sheet metal is not the only thing that can be bent on these brake presses. You can definitely bend thicker, beefier metal if that's what your design calls out for. I've bent, not me bent, but I've had in my designs up to 1/2 inch thick pieces of steel being bent, and I'm sure they can't do it on this machine to the right, but that 240 ton machine to the left, they'll bend that thing no problem, and I had no pushback from manufacturers with those. So just something to keep in mind. All right, so we're going to get more into bending right now, our types of bending. So there's standard tools is your V bending and your wiper die bending. These are going to accomplish most bends that you would need for standard, simple designs, and especially for low quantity designs. You're going to want to be using standard toolings, like I said, those brake presses previously. You want to be able to make sure your design can operate with those. Whereas custom dies over here, so like I said, these are likely custom tools because this width right here, this height right here of the die, or we're here to here, all of these are really going to impact how this guy actually bends and what your final shape is. This one right here, what angle are we putting it at, that distance right here, all these are going to be custom to your shape, your design. So if you have high output, high volume, it might be worth looking into doing 2 bends or 3 bends at once. So let me know, this right here, this shape, based on the height and the width right here that I'm looking at, could be made with just 2 bends. And same with this die over here. This can be made with 2 bends on a wiper die. or a single die all at once. So it really all depends on what you're looking for, what your volume output is, and the cost associated. So we'll quickly look at bending limitations quickly. So as I mentioned previously, could those double bends be made on a single bend, just bending it twice, or a brake press? Sure. But for complex and expensive parts, it's likely the tool can be made to accomplish bending. So you almost certainly will be able to make a tool that can do it, but it's ideal to allow bends on any machine, especially simple brake presses. This is just a general rule you should be following for all manufacturing processes, is that when you're designing something, you want it to be able to be made in as many shops as possible. You do not want to limit the method of manufacturing. All right. If I were to come up with a sheet metal design that was so complex, there's only one shop in the world that is even willing to make it, and it costs $1 million in tooling. All right, well, now if that shop goes out of business or they change their mind and say, I don't want to do it anymore, my design is over. I can't build it anymore. So you want to just avoid that. The more shops, the merrier. So we'll take a look quickly. This part right here, can we bend it into brake press? So it's all starting as just one flat piece right here. We'll bend here. We'll bend here. We'll see on the next slide what it looked like. So excuse my crude drawings. I did not have time to whip up an actual CAD model of this. So PowerPoint Paint is our friend today. So we're going to look at this right here. We're going to be bending right here, punch down, and this will be the shape that it comes on up in. Looks fine to me. I don't see any reason why they can't be bent. Move on over now to our second bend, and I think we can see we have a problem right here, is that this part right here is going to hit our punch. Now, is there a solution for this? Not with your standard brake press and brake or die. Could you maybe have a die that looked something like, I don't know. Maybe we have a die that looks like that. So now when our part comes on in and bends, we'll see quickly. Blue piece right here bends here. And then this purple part still has its clearance right there. And this guy right here is, sorry, wrong color. We're still bending right here. So this might be a way to do it. You might have trouble now removing it from the machine. I mean, obviously these things can spring around a little bit. But yeah, so it just goes to show that if you have this cup right here with a very deep cup, punching and bending it is just not going to be an effective method to get it done on your standard brake press die. So just something to keep in mind. Like I said, use standard tooling wherever we can. So we're going to get quickly into types of bending. I'm going to try to speed it up a little bit here. I know I'm talking too much. All right, so we have air bending, bottom bending, and coining. So air bending, you're going to have an air gap down here. This is the most common, especially nowadays when we've gotten a little better at our processes. So what's going to happen? So one thing's important, it's flexible. So you'll start off with this bar right here. It's completely flat. Then they'll punch it down. Maybe they'll move this thing down just a couple thou and move us into a small 1 degree angle. Sorry, maybe 1, 2 degrees. And the farther and farther go, the more and more you're going to bend this angle right here. So this goes back to why we don't really have maybe the most formulas for these kinds of things that we do, but they're not the most accurate, is the thickness, the grain size, the distance of this punch, all the opening of this die right here. So many factors go into what the final angle of this is going to be, because we can imagine this, this opening was much wider. We're going to get touching the parts here and here. It'll be a little less per stroke down of bend. So what they're going to do is they're going to bend it, get it. You say you want to get a 70-degree bend. They'll push this guy down, say an inch. They'll be at, 68 degrees. They'll come back, punch it down 1.01 inches, and now they're at 70 degrees. And then now for all future operations, they'll just punch 1.01 to start and get that 70-degree bend. So they'll just take a test piece and give it a go. So it's quickly air bending. Bottom bending is a little simpler. They're going to just send this punch all the way into the bottom, so you can just simply do a math out, say what's my thickness here, punch down until I have only the thickness left in that material. There's a little less spring back because you're deforming the material a little bit more to a higher angle. It's a little more accurate than air bending, but it's just a lot less common. Air bending definitely seems to be the industry standard. And then there is coining. Coining was previously used a little bit more. It's less common now, though. I think just since we have gotten air bending to be a little bit more precise and accurate. So the way coining works is you're actually going to be deforming the material. The punch is going to punch past the material thickness and really compress that material at that V intersection right there. So what that does is it allows there's no spring back in the material. You've permanently yielded the material here. It does not want to turn back into a flat plate anymore. Why we have been moving away from these machines is they're expensive. It's high hydraulic force, high forces to bend it, much higher than air bending. So it's a much more costly machine and process, and it doesn't necessarily produce better results anymore, especially not for the cost. So important thing to note, we've talked about it a couple times already, but now we'll just go into right here, spring bend back, or bending spring back, sorry. So as when the material bends and bounces back, so you see over here you have a bend angle that you actually bend it to, and then what the actual final angle that it bends at is. So what it is, if you want a 90-degree angle, you might need to bend it to 92 degrees. So we have common values down here. Once again, this goes back to, are there real formulas? Yes. Do you want to use them? Probably not. I would just use the industry standards and values from there. Couple things to note, just how it's happening. A larger radius, smaller angle. So if you can see right here, we're at 90 degrees difference here and here, but there's a lot of strain in that material in order to bend it right there. Whereas you can imagine if there's a very large radius, we're still at a 90-degree bend, but there's a much less strain in all that material right there. And then same for smaller angles. If we have a cantilever that bends down, say 1 degree, depending on how long this cantilever is, that's probably not going to permanently yield the material at all. Whereas if you have, say, a really short piece, small angle, it will bend it. Or say if we were going over to a full 90-degree bend right there, or even more, a lot of strain happening right there. So that's just why inherently you're going to have less spring back from that, because the material has yielded more. K factor, it's an important thing to mention. It's the ratio of the location of the neutral axis to material thickness. So this is used in a lot of designs. So we see this down here. This is from SolidWorks, sheet metal design. You put a K factor in right there, and then SolidWorks will help you figure out the rest of these values up here of bend allowance, bend angle, material thicknesses, or you'll be putting any material thickness for the CAD modeling, but inside radius, so that it'll help you bend properly and do all the math out there for that. I'd like to have done a simple hand problem, but it's a pretty simple formula up here we can see, and I think the big thing is that you need test data to get the values of K, or you need to find bend angle, you need K values. So there's just tables you can find online for standard K values. So we're gonna pivot quickly to just press selection of shearing, just to show how much low force bending is compared to these other methods. So shearing through material, it's just pretty simple, force divided by area. So we have this right here, our thickness, length to be shear, that's our area, this is the stress of the material. So 70 KSI, that's the ultimate, that's pretty common for 316 material. So we have our formula right here, it's just for a punch force. It's real simple. Statics, I'll point out there's a 0.5 used in here. If we all remember from our von Mises stress equations, there's a 3 here in our shear tensor. So that's just, when they're under the square root, the 3 there, 0.5 is what you'd reduce this value down for your allowable. I've definitely seen 0.6 used. It's a little more conservative, but the book uses 0.5, so we'll stick with that. So we're going to get into press selection, how we're going to select a press for bending, how much force is required for there. So we'll assume a 90-degree bend, assume R equals 2T, and then with that, we can say the math. It's approximately 5H, H being our thickness is over here. So the way this works is you actually just, it's a balance of energy equation. You'll find the strain on the outer fibers, find the volume subjected to the material bending, at which point you can then find the energy in there. From our strain and our volume, and then you can say, hey, the force of this guy right here times the distance, that's also energy. Set the two equal to each other and you find your force. So you can see that right here. We found our strain, we find the stored energy right here, and then we set that stored energy equal to the force times 5H, and we get our force for bending. So 550 pounds, if we remember back from our shearing, it's once again the same thicknesses and length. It was 3,500 pounds. So only 15% force is required for bending. So it's an important thing to note if you are selecting out prices for what you might need for your processes. It'd be important if you could ever come up with a situation where, hey, maybe you were going to use a shearing operation and bending, but if you can combine it to just use bending, that'd be great. So maybe we have an example right here where it's maybe an electrical board. There's a bunch of cutouts or bends for whatever purpose, but there's also a cutout right here for a cable. Maybe you could use that, punch that tab out, so you still have a area for the material to be removed, but you're not actually, shearing that material away or anything. Thinking about it now, this is not a good example because these holes would need to be water jet cut, or these tabs would need to be cut before bending them, and you could just cut this hole out. So yeah, I'm trying to think about right now if there's ever actually a real instance where you would be able to substitute a punching shearing operation with a bending operation, because you're always going to have a cutting operation beforehand. So it's maybe not the best example, but it's something to think about. If anyone has an example they've ever used that for, I'd be happy to hear about it. So an important thing to keep in mind is the stress in the bent part and accounting for it in your design. So when you're bending your material is plastically deforming. So for things like right over here, we have this electrical junction box. That's acceptable. We don't really care about the strength right here. It's not holding up much weight. It's really just keeping your electrical cables all together in a nice little area, and let's say that's a junction box. But then you're gonna have items down here like your springs. Springs need to have elasticity. They need to have very specific elasticity in order to meet the values that the designer wants. So after bending these guys and permanently yielding them, you're not going to get a spring anymore. So you need to put these through a secondary heat treatment process. That's normally a pretty simple process due to a pretty low volume of this material. These springs will heat up to high temperatures quick and then cool down quickly. So it's not a very high energy heat treat process like it would be to heat up a 1-inch thick hunk of steel. So one thing I just want to point out, is materials for sheet metal. I know we keep saying sheet metal right here, but are there other materials that can be utilized in a bending process? I gave a little bit of thought into this one. The only one I could really think of was some plastics, and definitely I found some instances online where you would actually be bending plastic rather than just injection molding it or other types of manufacturing methods. So for this one here, we would just heat up the edges and bend it around a table. No special forces, no manufacturing methods. It's really low force, so it's something to keep in mind. So we have a couple of guidelines right here, and then we'll be ending on up. So avoid small holes, narrow cutouts. So fragile punching tools that would require also potentially deforming your parts, breaking your parts due to low wall thicknesses. So like you can see right here, if that was a really thin wall right there, and you try punching these two pieces, there's a chance that wall will just shear right on out. So this part right here, I described it from the book. All of these figures, A through E, should be 2x the material thickness in order to not have to deal with any of these fragile parts or fragile low wall thicknesses and things like that. So just some good rules of thumb to keep in mind. If you're ever doing a raised boss like this right here in a sheet metal design, some simple formulas right here. Like I mentioned, that's generally how a lot of these designs for sheet metal works. Is there's these standard tabs, standard features you are going to be putting into shapes, and then there's standard formulas and standard math values in order to ratios and stuff in order to allow for the designs to be made without bending or permanently breaking the material or having to do too much complex analysis on how to do it. When we talk about sheet metal, is about being cheap and fast and quick and effective, and if your designing and engineering time takes a lot of effort, we're going counterproductive. So the engineers should be using these formulas. We should be using these quick values because it's the fast and cheap way to get the process figured out. If you really need to go through and do the math every time to figure out what this H to L ratio is, you're better off just machining it probably. So a quick conclusion slide. Sheet metal design generally follows guidelines, not as many formulas. So industry standards, they're great to be using. So you say proper bend radius, common dies, proper hole features, proper placement features, use industry standards. You don't want to necessarily have to go and do a finite element analysis to determine is your wall thickness good enough. No, just use your 2 times the thickness. We didn't get into it, but it's important to account for assembly and make sure any post-assembly bending can still have clearances. There definitely are times where you might need to assemble 2 pieces together and then bend them, or assemble them together and then punch them. So just be mindful of that in design. It's very important to account for plastic or elastic design, whether you need a secondary heat treatment process or not. Um, when I've been doing my research onto this, a lot of things people say, think flat first. Think of how your design is going to look on a 2D surface. They have like nesting softwares out there that'll help you out. Say if you got a triangle and maybe a square right here. Well, okay, how are you going to cut them? You're going to cut out a square first. Well, then you'll only need a one cut and two cut in order to make your triangle piece, rather than say cut and then a space and then a triangle piece right here. That's just not an effective cut process. So there's softwares out there that can do those. We didn't get into them, but they're pretty cool. As with all engineering, keep it simple, stupid. That really goes with sheet metal design. Do not overcomplicate your designs. Do not make them crazier than they have to be. Just simple bends, brake press bends. That's really why you want to be keeping your designs. And mostly, there's a lot more to sheet metal design. This is a whole industry that we barely scratched the surface of right here. This was ended up being around 30 minutes. Like I said, there's so much more to it. So I hope I gave enough for you to know that these are things that you need to consider when doing your designs and have a starting point for how to consider them. But ultimately, there's a lot more considerations that need to go into sheet metal design. So thank you. Thanks for your time. Please post any comments. Definitely let me know if I screwed anything up in this video. I don't want to be putting false information out there. So yeah, let me know. Thank you. Have a good day, everyone.